Well, welcome back everybody. If you recall, before the world went apocalyptic, we were discussing buffer solutions and calculating pHs of buffer solutions. And a buffer solution is a weak acid in solution with its conjugate base. An appreciable amount of each one, so we can't ignore one and do things a little bit more simply. And when we have a buffer solution, that buffer solution has a pH that's governed by the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation says that the pH equals the pKa of the acid, so the acid form of the conjugate acid-base pair, and a correction term plus the log of the concentration of A minus over the concentration of HA. So if we know the pKa of the acid that we're dealing with and the concentrations of each of the conjugate acid-base pair participants, then we can figure out the pH of the buffer solution. Keep in mind, as I mentioned in class, that this term can also be done in moles. So moles of A minus over the moles of HA. So we use this equation to figure out the pH of a buffer, or if we know the pH and these concentrations, we can figure out pKa or any combination of those. Sometimes we're calculating concentration, sometimes we're calculating pKa, but most of the time it's a pH calculation. So those problems work very much like this one. So let's say we have a solution that is 0.180 molar HA and 0.850 molar A minus. If the Ka is 7.1 times 10 to the minus fifth, calculate the pH of that buffer. Well, we have everything we need, but maybe not in the right format because we have Ka instead of pKa. We'll need to know what the pKa is. Remember, that's a negative log of Ka. So we take our Ka from our problem, 7.1 times 10 to the minus fifth, hit the log button and flip the sign, 4.15. That's our starting pH for the buffer. We kind of call that a starting pH because back in our Henderson-Hasselbalch equation, when A minus over HA is 1, when both concentrations are the same, this whole term cancels out because the log of 1 is 0. So the pH equals the pKa. So this term accounts for the adjustments necessary for the differences in A minus and HA concentrations. So we plug all of our information now into the Henderson-Hasselbalch equation. pH equals the pKa, 4.15, plus the log of A minus up top, 0.850, over concentration of HA, 0.180. Don't have to worry about the units because they're going to cancel there anyway. Nobody ever really writes those in. And so when we typed this in back in class, when you were all here the last time, I recommended that you type in the log term first into these calculators. So 0.85 divided by 0.18 equals, I got 4.72 on my screen. Take the log of that, 0.674. And then add 4.15. So I get a pH of 4.82. And also, like I mentioned back then when we worked this kind of problem the first time, make sure that your pH went the correct direction. So the pKa was 4.15, and there's more base than there is acid. That means our final pH should be more basic than the pKa. If this had been the other way, where 0.18 molar up top and 0.85 in the bottom, more acid than base, we would have gone down from 4.15 because of that. Make sure that you can work these problems and get my answers before you try the more challenging ones, okay? Good luck, folks.